Yeah, you're good to go.
Perfect. So I guess you can hear me, you can see my slides, and you can see everything. Okay, great. So let me move this out of the way. Okay. So first of all, let me thank the organizers for putting this together and inviting me to talk here today. The work I will present is based on this paper here, which came out this June in collaboration with Alberto Castellano and Luis Ibanez. So without further ado, let me introduce you to the protagonists of today's talk, which will be higher derivative corrections. The structure of the corrections that we will look at is, as you see on screen, where f is a moduli-dependent Wilson coefficient, and the operators that we will look at are contractions of Riemann tensors. So we will really focus on the gravitational sector of the EFT. So of course, in general, computing these corrections to the two-derivative action is quite hard. However, there are special cases where we can look at protected operators, be it by supersymmetry or because they're single loop exact. Or in general, we will specifically select all those cases where both perturbative and non-perturbative contributions are controlled. I don't need to stress to this audience why this is quite important, as these coefficients, when computed and give us an exact result, probe quantum corrections even in the interior of modular space, which is a largely unexplored area. Also, one can use these Wilson coefficients to probe the quantum gravity scale defined like this. This is also a set of authors and works that have talked about this quantum gravity scale. And this is a non-exhaustive list. So if I've missed someone, I'm really sorry. Okay, so let me then introduce the main statement, which I will try to motivate today. The main statement being that in string theory, these Wilson coefficients obey Laplace-like eigenvalue equations over modular space. Here by Laplace-like, I mean simply that they involve an elliptic differential operator. Now, most of the times, this elliptic operator will turn out to be the Laplacian, but there will be important exceptions that I will talk about in the next 25 minutes or so. I will also try to argue that this has a non-trivial interplay both with dualities, and in particular dualities of the supergravity theory, and with the distance conjecture, in particular the exponents of the distance conjecture. Here I've given a one-liner of what I mean. So this exponent here, lambda, which we will talk about extensively, controls indeed the decay rate of this massive tower of states as we go towards an infinite distance boundary. Of course, since we've seen that starting from this coefficient, one can define the quantum gravity scale, we can expect consequences for its modular dependence. Let me then briefly review how people think about its modular dependence, at least asymptotically. This information is encoded in these quantities here, called species vectors, which are defined in terms of this logarithmic derivative. The idea being that their length gives us this exponential decay of the quantum gravity scale itself. What one can do then is to restrict in a certain asymptotic regime where one has a weakly coupled description, compute the species vectors there, and try to switch to another asymptotic regime. Perhaps the weakly coupled description will be different and related to the first one by a duality transformation, but still one expects that we can compute the species vector for each duality frame and then try to paste them together to give us a global picture. The resulting shapes are called species holes, and they moreover turn out to be convex. Great, so now I will try to convince you of the statement that I presented before, mainly by experimental evidence, in the sense that I will look at a plethora of string examples in various dimensions, and for each one of them, I will try to argue why the condition holds and what consequences it brings. So let me start with a simple class of examples that is maximal supergravity, where here, by maximal supergravity, I simply mean M theory on a big D-dimensional torus. The structure of modular space is given by this double quotient, where this GDR factor is a non-compact group. The GDZ is the same group over the integers, and K is the maximal compact subgroup. This GDZ factor is the U-duality group of the supergravity, which will be really important in the following, and has as subgroups both the T-duality of each of the circle factors of the torus and the large diffeomorphisms. In this context, we will discuss the R⁴ operator, which is the leading correction to the classical action, which has been computed in this massive series of works to be the Eisenstein-Langlands series. So we don't actually need to know how these series are defined, but we need two properties. The first one is that these coefficients are automorphic, and I will use automorphic in the following to mean always duality invariant, even though in principle it can be also used to mean duality covariant. And then that they satisfy this equation that you see on the bottom. This equation here can be derived by imposing that the supersymmetry algebra closes when in presence of these higher derivative corrections. So in this very simple class of examples, this is entirely determined by supersymmetry. Although we will see later that lowering the amount of supersymmetry doesn't make a big change. Okay, so I've left out on purpose two caveats. So as you can see by this big asterisk, I will postpone the discussion about 2A. That is because the duality group there is trivial, and I will discuss it separately. And the second caveat is that this equation here is not an eigenvalue equation in all dimensions. In D equal to 8, because the R⁴ operator is marginal, we have this special contribution. And I will come to this once we discuss the 4-dimensional case later on. In the meantime, let me then take as a case study type 2B. The duality group is given, of course, by SL2Z, and the modular space can be taken, for example, to be the fundamental domain on the upper half plane. The coefficients here are given by the more familiar non-homomorphic Eisenstein series, and in particular, in this specific example, the Eisenstein series of order 3/2, which obeys this kind of eigenvalue equation. There is a nice interpretation of this eigenvalue equation in group theoretic term by noticing that the Laplacian is nothing but the Casimir of the isometry group of the classical theory. And here what I mean is simply that if you compute the Lie algebra element of SL2R, and you compute the Casimir, and you check how it acts on this space, it acts precisely by the Laplacian. Another remarkable property is that these Eisenstein series contain constant terms. In particular, you can see it from this decomposition, which can be thought of as a twofold, let's say, expansion, either by taking a large tau 2 expansion or by taking a Fourier expansion with respect to the axiom tau 1. Notice that these first two terms thus give us the zero mode contribution, the shift symmetric contribution, and hence the name constant terms. It is also interesting to remark that this 3/2 here is quite important because it is related to the refined distance conjecture through the usual relation with the quantum gravity scale. This tells us that the exponent here should be 1/√d - 2, which in this case is 8. And this coefficient here is precisely related to the 3/2 that you get here. Great, so now what we can do is try to reverse the logic. So we can take the Laplace equation and impose it, trying to solve it for an asymptotic ansatz. We take here an asymptotic ansatz which is compatible with the distance conjecture, and moreover, we take axioms to 0. The reason here is twofold. First, we want to connect with the existing literature on convex holes, which always consider rectangular tori, so all axioms are off. And the second reason is that the constant terms that we want to, let's say, imitate are precisely the zero modes of this Fourier expansion. One can then compute this equation and see how it acts on our polynomial ansatz in tau 2. It acts as a simple algebraic constraint, which gives us as two solutions precisely the exponents of the two constant terms of the Eisenstein series. More geometrically, we can see this as a constraint on the species vectors, which in this very simple example are given by lambda, or rather are proportional to lambda. Notice also that the ansatz that we provided is not duality invariant. So we have, by choosing the asymptotic regime, we have chosen a duality frame, and thus we can switch duality frame. Here, this means simply doing an S transformation of this kind. This Z2 transformation here is nothing but the subgroup of the duality group, which fixes the tau 1 equal to 0 slice of modular space that we've chosen. So we have these two equations in two duality frames, and we can try to glue them together in one image, where notice that together with the right exponents of the Eisenstein series, we also get these two outer points, which make up precisely the type 2b convex hull, and in particular the species hull. Okay, so this example is very simple because everything is, let's say, aligned. So one can go down in dimensions to 9 and 8. If one applies the Laplace equation in 9 dimensions, one gets this upper bound on the length of the species vector, which precisely recovers the upper bound proposed in this paper here. So this is very nice. In 8 dimensions, one can still get an upper bound, even though it's weaker than the one on the left. Nonetheless, one can play the same game. So again, plot the Laplace constraints, which in this case would be circles, and plot them for every duality frame. So in the 9-dimensional example, the Laplace circles are given by this yellow and pink one, and they are related by a Z2 transformation. In the 8-dimensional case, things are a bit more involved because the subgroup of the duality group that we consider is quite large. So for visual clarity, I've just pictured the Z2 times Z2 subgroup here. Notice that both in 9, 8, and 10 dimensions, the outer vertices of the species hull always lie on these Laplace hyperspheres. Great. So all in all, what we've seen in this class of examples is that by imposing the Laplace equation and providing an asymptotic ansatz compatible with the distance conjecture, we can get constraints on the species hulls. But actually, one can do a bit more, because at the end of the day, these asymptotic ansatz need to be glued together also in the interior of modular space, and we must do so in a duality compatible way, and in a way that satisfies the Laplace equation even in the interior. So for example, for type 2b, in the case of SL2Z duality groups, one can uniquely identify the Eisenstein series of order 3 halves as the unique solution of this Laplace equation. So we'll see another example of this in the 6-dimensional case. Great. So let me then address the first caveat, which I left out, that is type 2a. In type 2a, the duality group is trivial, but the coefficient can be related to the one of type 2b. And in particular, we just simply have to delete the instanton contributions from the coefficient. So it agrees with the constant terms that we've discussed before. And one can, of course, brute force this kind of equation and check that it holds. From a more string duality point of view, this is simply related to the duality of type 2b by taking the Laplace equation of 2b and stripping away the axioms. We can be a bit more systematic, actually, and try to build the duality by compactifying on a circle R and use the Laplace equation in 9D, which we know it must hold, and the fact that the two coefficients are related in the limit. If one does this, then one recovers the same equation. This is basically implementing type 2b, type 2a duality. Notice here that this elliptic operator is not the Laplacian, but it's this Laplace-like operator because of the presence of this linear term. And notice relatedly that the naive isometries of modular space are not symmetries of the classical action. Here, what I mean is simply that if I look at the kinetic term of the dilaton, and actually this will happen in all one-dimensional modular spaces, there is a shift symmetry that naively I could associate with this field. But of course, this is not a symmetry of the type 2A action because there are exponential terms in this dilaton. In this case, the Laplacian would be the Casimir of this shift symmetry, but the presence of this linear term signifies a departure from this symmetric case. And as we'll also see in another case, this will be the same every time the elliptic operator differs from the Laplacian on modular space. Okay, so one thing that we can do now is to lower the amount of supersymmetries. In particular, we've seen that the equation that we discussed is simply a consequence of a supersymmetry with 32 supercharges. So we can actually go down and see what happens to higher derivative coefficients there. As a simple example, let us take type 2A on an Enriques-Calabi-Yau threefold. So this is a 4D n equal to 2 theory, where the higher derivative term that we will consider is this R squared term. And in this case, the coefficient only depends on the vector multiplets. We don't need to know the actual details of this threefold, but just that it's the simplest example where the topological string can compute this coefficient. And this computation involves solving an holomorphic anomaly equation on this vector multiplet moduli space, which has this form. R mod here is the curvature on moduli space. And in this particular case, it's a constant. So the right-hand side here is a constant, and this reminds us of the second caveat that we left out. This is, of course, due to the fact that both the R to the 4 operator in 8D and the R squared operator here are marginal couplings. And in particular, I will try to argue that these contributions are due to massless modes, so field theory-like contribution. To convince you of this, I will simply take a large Saxion expansion of the coefficient, which is made up of this, schematically, of these three contributions. So first of all, we have a constant term-like contribution, which again is shift symmetric, so it's written only in terms of the Saxions. We have Walsh instanton corrections, and then this kind of logarithmic term. Now, these log terms that appear in the coefficient are the same log contribution that we expect from field theory loops. And this is corroborated by the fact that these couplings are marginal. Interestingly, notice that this log here is the contribution that solves the particular equation, so the one with the constant on the right-hand side, while the other terms satisfy the homogeneous equation. So in the case of marginal couplings, the statement about these coefficients restricts to the threshold correction. That is, we must neglect the massless contribution, the field theoretic contribution. Great. So now one can play the same game that we did as in type 2B. We impose the Laplace equation and we provide an ansatz compatible with both the distance conjecture and by switching off axioms. If one does this, one gets that the coefficient at large Saxion must be linear for every Calabi-Yau threefold, and thus we reproduce this asymptotic behavior together with the holes of the theory. So now we can switch to a more involved example, M theory on a Calabi-Yau threefold. We look still at the same operator, so R squared, and once again, this operator will depend only on the vector multiplets. One can understand this from either dimensional reduction of the R to the 4 term, or by uplifting the previews for the example. Sorry, for the result. Either way, one gets, again, a linear function in the vector multiplet moduli. And although now we have an important difference. Here, the vector multiplet modular space is given by a constraint hypersurface. And as argued in this paper, this breaks the naive isometries of modular space. So we can think about a simple example to see how this happens. So in these simple examples, the modular space is, well, this homogeneous space is characterized by having SO2-1 isometries, but the tensor with which we write the constraint is, of course, not an SO2-1 invariant form, an SO2-1 invariant tensor. And this means that this kind of constraint breaks these isometries. Given our type 2A discussion, then we might expect that the elliptic operator does not agree with the Laplacian, but it's something a bit more general. And indeed, we find the same. And we can do so by performing exactly the same steps as before. So we compactify in a circle R, and we use the Laplace equation in 4D to uplift the operator to an elliptic operator here. And we get this equation where the eigenvalue is nothing but the number of vector multiplets. And the elliptic operator looks like this. So here we have a linear term defined in terms of this vector field P, which itself is defined in terms of supergravity data. And then we have this term here, which is written in terms of the normal vector to the constraint per surface. So we recognize this term to be nothing but the induced metric. And thus this first contribution is the Laplacian itself. So again, this is the same philosophy of type 2A, where the elliptic operator is given by the Laplacian plus a linear term. So lastly, to fill out the gaps of the 8 supercharges landscape, let me talk about 6 dimensions. And again, the same kind of operator, which again depends only on the tensor multiplets. So here one can compute it from the F-theory lift of the R to the 4th term. And once again, for the third time, one gets a linear function. The story is similar to 5D, where the tensor multiplet modular space is constrained, but now with an important difference. That is that the constraint is given by this SO1T invariant form. And of course, this preserves the naive isometries of modular space because of this invariance of omega. And so we might expect that the equation is given in terms of the Laplacian, which is precisely the case. And the eigenvalue is given by the number of tensor multiplets. So again, a very nice expression. One can then impose again this constraint bottom-up. For example, we did it for this simple class of theories given by Del-Pezzo surfaces. And the equation that one gets can be solved by standard methods using Legendre polynomials and imposing regularity over modular space, which must be imposed. We have that we recover the linearity of the coefficients in these tensor multiplet moduli. So this is the second example together with the type 2 bit where one can get more information by really insisting on imposing the equation over all modular space. Okay, so given this, I can conclude. So we have seen that in string theory, in various dimensions, higher derivative coefficients obey Laplace-like eigenvalue equations over modular space. And this is also true asymptotically, even for generic type 2 theories, which is something that I did not have the time to discuss here, but is present in this paper here. And this is a Walesy computation, so you can take really a generic CFT. And we've seen also that this has consequences on the modular dependence of the quantum gravity scale. We have also seen that imposing the Laplace equation with a constant term like ansatz compatible with distance conjecture, one can extract asymptotic information of the coefficient. And if one insists on really exploring the interior of modular space, then one can also get, in some simple cases where we know how to solve the equation, more information. So notice that I did not talk about what is the physics behind the condition. This is because I don't know. But have a work in progress here with Muldrow, Bernardo, Sanjay, and Alex, trying to link these kind of Laplace equations with the an Hamiltonian of the quantum mechanical system of a particle over modular space. And this is, for example, something that happens when you compactify the theory of 1D, and you interpret the resulting 1D action as the wordline action of that particle. Another interesting link is with membranes, with tensions of specific class of membranes, as discussed in this other paper here. or by geometric flow equations. Another interesting possibility is that if I take the equation at face value, this resembles a steady state equation. And given that these coefficients sometimes predict the entropy of black holes, there could be some nice thermodynamical interpretation of this. Lastly, one can argue that these eigenvalue equations, these differential equations, can be also used to compute the complexity of these coefficients, which goes in the direction of the tameness conjecture. And to end, we also have no clue what the eigenvalues mean. We have simply computed them here and taken them as granted. So except for the case of marginal couplings where we know that the eigenvalue is 0 because of these terms which are constant on the right-hand side, for the rest of the cases, we really have no physical intuition. So with these few comments, let me conclude and thank you for your attention.
Thank you, Christian, for the very nice talk. Are there any questions from the audience? Yeah, I see a question from the Max Planck group. Please feel free. Go ahead.
Very nice talk. For these elliptic operators, do they become asymptotically just the regular Laplacian on moduli space?
So yeah, we have checked the 5D examples, for instance. And indeed, there you can show that asymptotically there is a Laplace equation that holds. The problem is that the eigenvalue is not the same for different asymptotic regimes. So you really have to see how this reduces given the limit. But yes, okay, in principle, yes.
That's interesting, because if the species scale is some nice function of the moduli asymptotically, but then is also an eigenfunction of the Laplacian, then the eigenvalues tell you stuff about the curvature, like relate the curvature of moduli space with the species scale. And I don't know, have you thought about connecting these Laplacian or differential elliptic operators, the curvature of moduli space?
Yes, so we have thought about this, but the problem here is that this is what I'm making is not a statement about the spectrum of the Laplacian on these moduli spaces, which would be more suitable to discuss the curvature, for example, because there are relations between curvature and like upper or lower bounds of these Laplacian eigenvalues. Here, I'm simply taking an eigenvalue and then computing the consequences for the species scale.
Okay, thank you.
Thank you for the question.
And Nacho, if you have a quick question.
Yeah, it's super quick. Okay, Christian, it was a very nice talk. I just have a super simple question that probably you can answer. When you plot like these circles that you have from like solving the equations that you recover like the convex hull, what's like the way that you do that? Because I guess why do you get like a single figure and not like many other possibilities?
Yeah,
by
so
touching where they intersect. Yeah.
Yeah, so exactly. So the reason why I get these hypersurfaces is because I take ancestors of this kind, and all equation does become algebraic. And if you does this equation define like hypersurfaces on the tangent space of your slice of modular space? And here, for example, I have multiple constraints which are always related by dualities, right? So you can plot them in the same image. Is this what you're asking, or?
Yeah, but for example, there's if the other point on the left of like the theory one, why, for example, you don't take that one?
Yes, so good. This is like it touches precisely. So we do not remove all the generalities. Like we do not fix one convex hull given simply the equation. We have to make extra assumptions. So for example, here, if you just impose the Laplace equation, you get the upper bound on the species length vector. But then you have to, for example, to single out this point here, you have to impose the Laplace equation in 10D, for example, for type 2B.
Oh, okay, so you do it like in a more recursive manner.
Exactly.
Okay, yeah, okay, then I understand. Thanks.
Thank you.
Okay, thanks a lot. So I have to cut short the discussions. And if there are more questions, please stay back after the next talk, and we'll ask the speakers to stay as well for a couple of minutes. So I'm going to stop the recording now.